All right, let's get started. This is our day 9 of CS147. And we have 34 participants so far. That's good. So tonight's topic, actually it's lecture 8 and split between two parts. Actually, next 2 days we'll be studying this. We start with a sequential circuit design, the methodology of it, how do we, from a given problem statement, how do we solve it using a sequential logic. That's the first topic, and then we'll move on to the uh, commonly used components, digital components like decoder, multiplexer, etc. And then we'll move to more complex component like a register file, and different type of register configuration for the shift register, etc. that we'll be reviewing. And then we'll end up with an combinational bit shifter, which supposed to be faster in operation compared to the register-based shift operation. I hope you guys have reviewed the first part as I suggested. If you have any question at this point, let me know. And let me also check the discussion if there is any. Nope, there is none. No questions so far. Interesting. Okay, let's start with again some Verilog simulation example of some of the circuit. Especially, it will be interesting to see how it works in life. So what we have read so far is this problem, right? This is the problem we did as an example in this lecture. And from a given problem, which basically recognizes a pattern 1101, if per clock cycle, if this comes into a circuit, we should be able to recognize an overlapping 1101 sequence. So that's what, from here, we first created the state diagram of that to solve that problem. This is nothing but that finite automata concept. Any computing system, however complex it seems like, it's at end of the day, it is a FSM, finite state machine. So this is just a little concept there, a very small finite machine which we created. And now from here, once we created this FSM, how we can implement in a digital circuit, that's the discussion point here. So from these, we create something like state table. Okay, from the state diagram to state table, from state table, then we do some state assignment and change the state table, instead of literal state names A, B, C, D, etc., replace it with its bit representation of the state. And from that state table, we then construct the truth table, corresponding truth table out of it, with the state variables. We mark it as a ATBT, and then next state, that same state variable AB, next state in the truth table, we mark it as a AT plus 1, BT plus 1, and the primary output is a Z that we do. And then from there, it becomes like a combinational circuit methodology. We devised a truth table for each of this output. One part is a state output, AT1, BT1, and sorry, AT plus 1, BT plus 1, and another is a primary output. So we have three truth table with a function there, the function of AT, BT, and X. And for the state equation, state variables changes, we, instead of like saying it as a function f of AT, BT, X, we mark it as a DA, just as a convenience to make sure we use a D flip-flop there, nothing else. Like you can just name it anything there. but it is an DA. I name it as a DA to make sure, to denote that I'm going to use a D flip-flop to actually store this state in this finite state machine. So that's what the DA significance is and DB significance is. But ultimately, it's a function. We put it in a SOP form, and from there, we basically came up with a logical expression, logical equation of them. And then what we did, we basically used the D flip-flop for, in place of this equation with that function DADB, and its output of that flip-flop is basically your present state variable AT, and the input of this is the next state variable AT plus 1. And there the functionality of the AT plus 1 based on the AT, BT, and input X is derived there. Similar for the B flip-flop. And from there, we claim that this circuit will serve the purpose which we supposed to do in the given problem. Now let's simulate in the model sim. So I have some code here, which let me show you. First of all, I made a, remember last time we made a negative edge triggered flip-flop. Now this time I also came up with a positive edge trigger flip-flop with this simply DFFPE. That is the component I used, and it is basically that clock configuration is just opposite to that of the flip-flop. And also, instead of positive edge preset reset, I went for a negative edge preset reset in this case. That's why I marked that name as a N preset N reset in that order. But it's practically a positive edge flip-flop with a preset reset. And hey, what did I use, by the way? I used DFF. Let me see what is that. C bar goes there. Oh, actually, I used a negative edge machine there. Interesting. Anyway, so that's we'll see in the simulation what happens there. But anyway, but it's basically representing this circuit. Let me try to put it side by side. Okay. So your DFFA is a function of the output from, okay, here is your D, right? Input to the DFFA, which is ATP1, okay, which is ATP1. And ATP1, let's follow that. ATP1, what is the ATP1? Here, this is a word which is this OR, output of this OR of W1, W2. I think this is this OR, and then, okay, so we covered up this OR here. Okay, so this output belongs to that output of the OR, and then we have AND1 and AND2, which is ATBT. So this is ATBT. So this AND is basically combining AT and BT. So this is AND01, and this AND is combining X and BT. Yeah. So this is another. So this output ultimately goes as an input of the flip-flop A. So this is the connection. And I set the preset as 1, means I don't want to preset, only I want to operate on the reset. Similarly, for the next one is the similar thing. And here, BT plus 1, this output is directly coming from the X. So that's what my connection is. D is connected to X clock, and then we have the AT bar, BT bar, etc. Those things are output coming out from the flip-flop. And last but not the least, the output function is implemented with this 3-input AND, which is AND O3, which is AND between X, BT, BT bar, so this guy, and AT. So this is what happened, like X, BT bar, X, BT bar, and AT. So that's the whole circuit implementation of that. And then I have a test bench for this one. This one, what I did, I just selected a random pattern there. Okay, first of all, I instantiated my machine, recognizer 1101, and simply drive and register X onto that with some clock. Remember our clock generator. That's our simple clock generator. And N reset. Initially I set it to 0 to reset the state, and then I made it to 1. And then what I did is feed this pattern bitwise. So I initialize the pattern, which is an integer type. And that integer value I defined as a 32-bit binary, followed by this 32 of them. And then I said that while the pattern is not 0, means unless this pattern become all 0, what you do each 10 nanosecond, you pick up the MSB, pattern 31-bit, that is the MSB, put it into X, and then left shift the bit pattern by 1 bit. So each 10 nanosecond, I'm going to left shift this bit pattern to grab those patterns grab those patterns from this variable to feed into X, store into X. So essentially, I'm sending into my machine as a pattern of 101, 101, etc., etc., etc. So we compile it and let's see how it works. Recognizer TB, here it goes. And let's input them right away. Okay, let's rearrange. Reset goes up, X and Z. Okay, let's simulate. Run all. There it go. End of the story. Okay. So pretty much we have some clock coming out, toggling each 5 nanoseconds, and then we have some bit pattern incoming part time. So if you see, we have possibly recognized 1101 successfully in this machine. Let's say it becomes like 1 here, 1 here, 0 there. Is it 1, 1, 0, and 1? Okay, so, and then 1, and as soon as it goes to 1, your recognizer actually goes to high, right? And then it went down, and then let's see, get some more bit pattern, and seems like here it recognized it. So it's 1, 1, 0, and here it goes to 1. So at this point it becomes 1, and then it is 1, 1, 0, 1. So at this point it is also 1. So it actually recognized that overlapping 1101, which is probably here. 110. Oh, where is my overlapping? 1101. Oh, there. 1101, and then overlapping 1101. So this is the scenario there. And then we have at the end, towards the end, we have another 1101, 1, 1, 0, sorry, 1, 1 here, 1, and 0, and 1. So there it goes and have that high, it's recognizing the X. So seems like this circuit is okay to recognize the incoming bit pattern in a sequential way. All right. Hey, questions so far from anyone? Okay, then we move on to our next component in our study is a decoder and multiplexer, and let's simulate them through our simulation environment. Let's end this simulation. And then we have a decoder, simple decoder. It is a like 2 to 4 line decoder. Input as A0, A1, and output as M0, M1, M2, M3. And we basically, where is my decoder here? Exactly had these, no, not this one. This is with the enable. Is it? No, yes. Yeah, this is with the enable. So I think this one. This is the decoder, and I'm looking at this truth table to see if we can actually validate the functionality. We have these two inverter here, and then 4 of this AND, which are basically combining different logic values carried in the wire A0 bar and A1 bar. We are combining them to grab those logic output values. And I have one test bench for it. It's a very simple test bench. I instantiated that line decoder, and I have defined an array of register 2-bit. That's what I'm connecting here, A0 to A subscript 0 and A1 to A subscript 1. And then there is an array of where, which is like 4-bit, and I'm connecting those 4 bits individual array element that is which are individual wires into this port of M0, M1, etc. This is just for to less typing. You can actually define different wire names there, no problem. Then in a loop, okay, start with A as 0, like integer 0 means actually in a 2-bit form it is 0, 0. And then for I equal to 1 to 16, every 5 nanosecond, I'm assigning A equal to I. Now, remember, I is an integer type, which is successfully will count these all 16 values. But being A as a 2-bit, it will be rotating between 0, 1, 2, 3, and then become 0, 1, 2, 3 as we assign this large number of bit into a smaller number of chunks. So it will be truncated. The value will be truncated. It will just pick up the last 2 bit from I and assign it into A. And after that, simulation stops. So with that, let's simulate it. Line decoder TB. Where is that line decoder? Oh, here. Okay, and then let's just concentrate on these 4 signals. 2 input, 4 output from it. Add it to wave. And simulate. And simulate. Okay. So you see that as it was looping with this 1 to 16 value, your A0 is pretty much like almost like a clock signal. It's regularly changing, toggling between 0 and 1. And thus the A1 as well. It is toggling between 0 and 1 with a lower frequency, but somewhat they are repetitive signal because I am basically looping through the 16 values and assigning the last 2 bits onto this A. So that's what the significance is. However, let's see what about that M0, M1, M2, M3 with respect to this truth table, right? So my 0, 0, which is supposed to give M0 as 1, just, oops. Okay, yep. 0, 0, M0 as 1, that's what we are getting, and everything is 0. Then A1, 0, M1, A0, 1, which is supposed to give M1 as 1. That's what is happening. M1 is 1, everything else is 0. And then the other one, which is A1 as 1 and A0 as 0, which is supposed to give M2 as 1, which is happening here. Exactly M2 as 1, and others are 0. And M4, the last one, is basically both are 1. A0, A1 are 1, and M3 is 1, everything is 0. And then it repeats for the rest of the time. The same patterns goes on. But here we can see and validate successfully that our decoder implementation works as we expected. It follows that truth table. So that's correct. So this is how we are at the gate level. We are defining the line decoder, 2 to 4 line decoder. Question? Okay, then let's move on to the multiplexer. Okay, so multiplexer, we did like this. I have a couple of components there. So here is that 1 bit 2 by 1 multiplexer. Okay, and here what I'm trying to do is, sorry, this is 1 bit 4 by 1 multiplexer. That's what I'm defining here. Okay, 1 bit 4 by 1 multiplexer. So each of these inputs and outputs are one single bit. I0 is 1 bit, I1 is 1 bit, etc. Output is also 1 bit, and S0, S1 is the selection bits. And inside that, I'm defining a line decoder, 2 by 4 line decoder, just like we did here. Okay, just like we did here. This is the 2 by 4 line decoder, which we already implemented in the decoder module. So I just instantiate that one. And like this diagram, I just go with that A0, A1 as a selection bit 0 and 1. We connect that, and output become my M0, M1, like this 4 bit, M0, M1, M2, M3. And later I use that to instantiate some of these 4 ANDs gate, and 0, 0, 0, 1, 0, 2, 0, 3. Individually, it connected to each of these output from the decoder with the incoming input line. And that become output from each individual and which I basically, for my code writing easiness, I just use that as an array of wires. Okay, it's just 4-bit array of wires. It become an individual bit. So each of this outcome is a E0, E1, E2, E3, etc. And then I used a 4-input OR, just like this get, to connect these 4 individual bits and get a 1 bit out of this one. Okay, so this is that 1 bit 4 by 1 multiplexer. Now I use that 1 bit 4 by 1 multiplexer to make it a 4-bit 4 by 1 multiplexer. Means Now each of these individual inputs are 4-bit, and output is also a 4-bit. So, underlying of this implementation of 4-bit of 4x1, underlying we have four 4x1 1-bit multiplexer. We instantiate 4 of them and connect each individual bit of this Y, I3, I2, I1, I0 to individual I3, I2, I1, I0 port of each individual 1-bit 4x1 multiplexer, and selection signal being the same. It is just 1-bit signal for this. I connected them all together there. So the purpose of having a 4-bit multiplexer is like this. Sometimes I see that student has this understanding of, okay, this is a combination of circuit and Y is nothing but a, a logic expression evaluation from the whole circuit. What is the selectivity of this? Why we call it is selecting between I0, I1, I2, I3? Why not? It seems like a very normal day-to-day combinational logic evaluation. It's nothing else. So on the 1-bit example, it won't be apparent, but its selection would become more prominent. Selection functionality would become more prominent with a multi-bit example. And that's why I bring a 4-bit example. In our case, we construct one 4-bit 4x1 multiplexer, and let's see if it selects the value successfully on the selection bit or not. And with that, we have the test bench like this. Let it come up. MuxDB. Okay. So Mux multiplexer test bench, I basically instantiate one 4-bit 4x1 multiplexer, and they are driven by 4 individual 4-bit input. So these are all I0, I1, I2, I3 are the registered 4-bit registers. And we have single bit for clock and selection logic. And then we have a outcome from that multiplexer, which is also a 4-bit. Then what we did is basically did something interesting here. Initially, we had the clock set to 0, S1, S0 selection bit set to 0. And then at 50 nanosecond, I changed the selection bit from S0 to 0 for being S0 to 1. And then after 50 nanosecond again, S1 to 1, S0 to 0. So essentially, this is selection of input 0. This is selection of input 1. Let me just write it down. This is selection, supposed to be selection of I0. And this is selection of I1. This is selection of I2. And with this, I select selection of I3. And then the data I am driving into the into this multiplexer between this I1, I2, I3, it's a little bit curious. It's always at the positive edge of the clock. I3 is assigned some random value bounded by 15, because 4-bit, I0, I1, I2, I3, they are 4-bit. That means their range is, unsigned value range is from 0 to 15. And that's what I did do that. Actually, I should have done it by 16, but anyway, it doesn't matter for the example. So this operation, modulus operation, would give me a result from 0 to 15. All right, now we compile it, and then let's see what is that mask selection operation looks like. Okay, now let's have all of them together, add into the web. Okay, and then move the clock up, selection signal up, and let it simulate. Boom, done. Okay. Now you see, till this 50 nanosecond, till this point, I had selection of bit of 0, 0, which means I need to select the I0. Now let's see, I0, follow the I0 and Y. See, they're exactly matching. Okay, they're exactly matching, except at the point when the selection become 1, 0 and 1. Now it starts selecting the I1, right? 4 hex 5, 5, 2, C. Now it is following whatever value is being on the I1, it is following that. And then it was happy till 100 nanosecond. And then suddenly, boom, it starts following the I2 because my selection become S1 0 and S0 1. What is that? Yeah. Oh, no. S1 1 and S0 0. So the selection of 2. So at this point, from this point, it starts following the I2 till 150 nanosecond. And then it starts following the I3 because my selection signal is 1, 1. So it is following the I3 now from this point onward. It is following the I3 exactly like this is B, C, 5, E, 2, 8. So this is what meant by the selection. And this is what is used inside the microprocessor implementation very often, that it is kind of an hardware equivalent of switch case statement. Like if my selection is this, go and grab the value from that specific input and route it to the output. So apparently for the 1 bit, it may seems like it is just a pure combination logic evaluation, but functionality wise, this becomes more like an selection of group of bits together for the purpose of computing. So that's the selection operation for the multiplexer. Question? Nope. Okay. So you guys are good with all the projects, everything, theories? By the way, you guys need to start with the project 2. It's up from last week, I believe. And that project is almost like 100x difficult than project 1. Project 1 is just a starter and to set up your environment, simulation environment, to carry on with your experiment and the project. Now, project 2 is the real deal. We are actually going to define the behavior model of a tiny processor which follows the instruction set architecture of CS147DV. So please make sure you start the project now if you haven't started already. Otherwise, things will get difficult. Like, don't procrastinate at all. Like, I know like some student procrastinated on project 1 and had run eventually into issues. So please start early. And if you run into trouble, you can always come to me. And I also encourage you guys to work within your study group to solve any problem. Though it is an individual project and you need to write your own code, but you can help each other in fixing problems. And also you can share test bench with you, like for testing your modules. That's okay, as long as in the report, if you are referring you are putting the right reference into that. You can do that. You can share the test bench, test program with each other, and can help each other in fixing problem, also help each other in like finalizing the strategy. Okay, this is what the implementation should look like, design should look like, this is what you need to do, etc. You can work them as a group. But submission is individual code. You should not copy paste code from each other. You should not copy paste report from each other. That's the only constraint there. Is that clear, everybody? Okay, by the way, like in the project 2, once you go there, you need to download a package there. Project 2, it's I have implemented most of the codes. Only the meat part that you need to implement, and there is a guide PDF inside the package. Many students often miss that and scratch their head where to start, what to do. So let me share that with you and make sure that you're aware of that specific document. Just hold on. Let me go to the assignment, project 2. Hey, where is my project 2? There. Okay, share. There you go. Okay, so this is your project 2, which is due April 7. You can say, hey, there is a month and almost a week from now. Well, it's a complex project. Okay, you need to keep working on that every day, right? And that's why there are milestones which are not, by the way, graded, but it is more like to give you an idea that when to complete what in order to make sure you are done within time limit. So please make sure you when watch this video, project introduction, and then what you need to do is basically, I have also explained in the project guide as well, but let me show you what I explained there. Please go through that video as well, project guide. So you download it, okay, and open. Let's see. Okay, hold on. Share the screen. Okay. So you downloaded the project, and project came somewhere, let's say in the download folder. Okay, now you expand that. So they're already given some pre-code for you, some Verilog code, some two test program are given. You need to make sure you add more, because these two program only test subset of the instructions that is being implemented inside the processor. So make sure you actually cover up all the instruction with some test program. And then here is the guide. So please make sure you know that. And this one gives you complete overview, step by step, what you need to do from the beginning. So you have source codes given, okay? And then it says what you need to do. ALU, you can copy from your project 1. Let's have it, but there are some extension need to be done on the ALU. The output 0, make sure you implement that one in that new ALU. And then next step would be implement the register file. I have implemented the memory for you. So please look at that memory implementation. Register implementations is somewhat similar and less complex than memory. So please make sure you understand that and do it and test it as well. Register file. And then this is the most complex part, control unit. So you need to start implementing like state machine for these, and then add the control signals, generation, etc. So it describes all the steps and all the concepts there in this guide. So make sure you follow it. And also an important part on how you decode an instruction. Remember, like we were discussing that in the instruction decode register fetch step, control unit decodes the instruction. Here is one sample how you can decode it. The idea, so I have given this task. You can, by the way, use this task in your implementation to print the incoming instruction if you need to debug. But it is use the same tactics that you need to use to parse and decode the instruction. What it basically does is your instruction is coming in 32 bits, and it's basically slice and dice this 32-bit into different parts of the instruction. Remember, like R type has a little bit, is a format, like it has a group of bits for the instruction code and group of bits for the function code, then register numbers, and then it's a shift amount. And same instruction, if it is an I type code, then we split the field into different parts. So exactly that's what is going on here. So what I did, your 6-bit or opcode, RS, RT, RD are of each of 5-bit. Shift amount is of 5-bit. Function code is of 6-bit. And for I type, immediate is of 16-bit. And for J type, address is of 26-bit. And then by this instruction, right, we are grouping the opcode RS, RT, shift amount function. Remember, this is very much resemblance to the R type instruction. So these group left-hand side and right-hand side of the equation is the instruction. That way, what Verilog will do, will split up this 32-bit and assign them into corresponding register. So we just slice and dice that instruction. And similarly, same set of bit pattern, we sliced it into I-type instruction like this, opcode RS, RT, immediate, and then same instruction bit pattern onto opcode and address. Then how do we know when to use what? So basically then, as controller does as well, it looks in the opcode first and determine if it is a R type. How do we determine? R type opcode is always 0. So if it is a 6-bit 0, then look at the function and it writes the function there basically. But in your implementation, what you need to do as a controller is basically, if it is this function, which is basically I, that means like these per phases, remember this instruction fetch, decode, execute, memory, and write back. Controller issues different control signal to the different component, like to the ALU, to the register file, to the memory, etc. So now you need to consider that, okay, you have this R-type instruction, what action you need to take for the different states. If your machine is in proc fetch state, if this is this instruction, what you need to do. If it is in decode phase, I think this is independent of instruction, mainly the proc exe. Proc decode also, by the way, proc decode has independence on instruction. After parsing it, you need to see if you need to fetch from the register, and you need to give out the control signal for that fetching at this stage. Then proc execute, again, this same set of switch case statement would come in handy. In the exe state, okay, if my opcode is this, if my function is this, what I'm going to do, what the control signal I'm going to use. That's what you need to write. Similarly, if it is I type, then what kind of control signal I need to spit out from the controller to the other component. Similar for the J type. So for each state, similarly, wherever needed, I would expect you to put something like case switch statement, and case wise, you are spitting out the controls for the rest of the component. So that's the basic idea of the behavioral modeling of the controller unit, which is pretty complex. Please start ASAP, like today, tonight, probably, if you haven't started already. Question?
Professor, how soon do you think Project 1 will be graded?
We just have started. So the main time-consuming part is the report grading. Like we have quite a lot of report, like 56, 57 report, and yeah, a week and a half, maybe, or 2 weeks, let's say, max.
Okay, thank you.
All right, any other question? Okay, then if we don't have any other question, why don't we just take a break tonight, stop here, and go back, make sure you start on your project. Also keep on reviewing your labs, like they will help you in the project. All right.